So what we want to look at today are the derivatives of the 6 trig functions, and I'm going to go through proofs of most of these. But before you do that, you might just want to take some time just to consider each of these sort of visually. If, for example, I was wanting to know what the derivative of a sine x graph was, I could just take a sine graph. Okay, 2 pi there. Pi over 2 pi, 3 pi over 2, 2 pi. And I'm just going to sketch out the derivative graph. We've done this before with graphs where we try to sketch out what the derivative might look like. So we'll notice that on our sine graph the derivative is 0 at pi over 2 and 3 pi over 2, so we have zeros here. At 0, x equals 0, the slope of the tangent is, maybe it's 1 or so. So let's just say it's 1. And the slopes are decreasing down towards 0. So the slopes are decreasing. Then the slopes are becoming more negative until we get to the pi, and then the slopes start swinging back to be less negative towards 0. And then the slope starts swinging up positively towards some value here, which perhaps is 1. So if you look at this derivative graph, you might hypothesize that perhaps the derivative of sine is, do I know the shape of this graph? Well, it looks like a cos graph. So that would be a reasonable guess. Now we will see whether that's true or not by doing a proof of the derivative of sine x. And to do a proof, we always need to work through the definition of the derivative, which I have here at the top. So let's begin. The derivative of our function f of x sine x is the limit as h approaches 0 of sine x plus h minus sine x all over h. Now I know most of you have not studied identities yet, but I will just tell you that in terms of manipulating this expression, you can't simply multiply the sign through. So sine x plus h does not equal sine x plus sine h. You could just test that out with a few numbers and you'd see that in fact is not true. So what we need instead is we need to know what sine x plus h is. And if you look on your sheet of identities that you were given and look for the sine of a plus b, you will see that this is equivalent to sine x cos h plus cos x sine h, and then we got this extra piece at the end minus sine x, all divided by h. Okay, what I'm going to do next is, out of these two terms, I'm going to factor out a sine x. Remember, what we're trying to do here is manipulate this limit so that we can evaluate it. So I'm going to factor out sine x out of the first and last term. I'm going to leave the middle term the way it is. Alright, I'm now going to break this giant fraction into two separate fractions on the next line. And I'm also going to start just reorganizing it a little bit for convenience. Now I know that the limit of two things added is the same as the sum of the limits of those two things. And furthermore, the limit of a product is the product of the limits. So I can take this statement and proceed down to this statement. Now when you get down to this stage, hopefully you will see some familiar things. First of all, remember that we have proven in fact in a previous video, this limit to be 1, and also this limit to be 0. And you'll notice that up here we have the limit of sine h over h as h goes to 0. So that section is 1. And this section right here, the numerator is reversed, but that's not going to matter. That's still going to go to a value of 0. So what's going to happen is I'm going to have 0 times something else, which is 0. And over here, I'm going to have h going to 0 of cosine x. Well, that's not going to, h going to 0 is not going to affect cosine x, so that's going to continue to be cosine x times this limit of 1. And so we're evaluating this limit to come out to be cosine x. And of course, we have then shown that the derivative of sine x is, in fact, cosine x. Similarly, you could prove that the derivative of cosine x, I'm not going to do this proof, but in a similar way to what I did above, you could show that the derivative of cosine x is negative sine x. So that's another derivative you're going to need to remember. By the way, it's important to mention that these results are all with respect to x in radians. And you say, well, why radians versus degrees? Does it really matter? Yes, it does matter, because these fundamental limits that I used up above, these are both true with h in radians. Okay, these results were proven with that understanding. So when I talk about the derivative of sine being cos, that will be with respect to x being in radians. Just another way to look at it is if you have your sine graph and you're doing your rate of change, your slope, whether you're measuring your run in degrees or radians, would give you a different slope. So the slope that a particular derivative is giving you is with respect to a run which is measured in radians, because these fundamental limits which were utilized in the proof were all set up and shown with respect to radians. Alright, let's look at the derivative of tangent x. We know the tangent x graph, and so what we're going to do in this one is we could go back to the definition of the derivative, but what I'm going to do instead here is I'm going to write tangent x using an identity, which is sine x over cosine x. Okay, that's one of the identities on my identity sheet. And then, since I know the derivatives of sine and cos, since I just proved them, what I'm going to do is I'm going to use the quotient rule on this. And so the quotient rule, remember, was the bottom function times the derivative of the top minus the top function times the derivative of the denominator, all divided by the denominator squared. And the derivative of sine x, as we just showed in the previous question, is cosine x. The derivative of cosine x is negative sine x. And so in the numerator we have cosine squared x plus sine squared x all over cosine squared x. And you hopefully will recognize another identity here, that on the top we have a Pythagorean identity from your identity sheet. Cosine squared plus sine squared is 1. 1 divided by cosine squared x. And 1 divided by cosine, we know, is equivalent to secant. So 1 over cosine squared is secant squared. And that, in fact, is what the derivative of tangent x is. The derivative of tangent x is secant squared. And in a similar way, I could show the derivative of cotangent x to be the negative cosecant squared of x. So there's another derivative to remember. Alright, let's work with the derivative of secant x. Secant x is a more complex graph. To get the derivative, I'm going to write secant in terms of something I already know the derivative of, which is cos. So I know that secant is 1 over cos. And now I'm going to apply the quotient rule here. So here we go. The quotient rule says the bottom function times the derivative of the top minus the top times the derivative of the denominator divided by the denominator squared. Okay, let's simplify this. The derivative of 1, the derivative of a constant is 0. So that's cosine x times 0. So that's going to be nothing. Minus 1 times the cosine of 0. 1 times the derivative of cosine, we know is negative sine, previously proven, all over cosine x squared. So 0 times cosine is nothing. Two negatives become positive. And we have cosine squared x. Alright, we could leave the derivative like that, but what we actually do is we're just going to change the look of it a bit. So I'm going to break up this result into sine x over cosine x times 1 over cosine x. And I've done that, maybe you see, because sine over cosine I know is tangent, and 1 over cosine I know is secant. And this is the form of the derivative we typically use for secant. The derivative of secant is tangent x times secant x. And similarly, the derivative of cosecant x is negative cotangent x times cosecant x. Another one you need to remember. So we have 6 new derivatives to know, and now we can add to the fun by doing combinations of things. So let me just do one example where I'm asked to find the derivative of a function that involves the multiplication of 2 functions. So getting this derivative will require me to use the product rule. So the derivative is, and I'm going to apply the product rule, it's the first function times the derivative of the second plus the second function times the derivative of the first. And so y prime would be, the derivative of cosine will be negative sine x. So let's just put the negative in front of the whole expression. The derivative of x squared is the power rule, 2x. It would be good to write that in front so that we don't get the x as the angle mixed up with the x on the 2x. And that is the